Okay, so let's dive into the basics of network protocols. Basically, a protocol is like a set of rules that computers use to talk to each other over a network. It's kind of like a shared language. It ensures everyone understands what the other is saying. These rules dictate how data is formatted, what it means, and when it's sent, preventing chaos. Think about syntax, semantics, and timing. These are key components that make these protocols work seamlessly. Okay, so let's talk about the TCP/IP model. It's essentially how computers understand and agree on how to send information back and forth. Imagine it like a layered cake. Each layer has its own specific job. The top layer is where your app's live, like your web browser or email program. Then you have the transport layer, which handles reliable or quick delivery of data. Next comes the network layer, responsible for getting the data to the right place. Below that are the data link and physical layers, which deal with the actual transmission of those bits. It's a really neat system that makes everything work seamlessly. Let's talk about the TCP/IP model. Think of it like a carefully organized postal service for computers. It breaks down everything we send over the internet into 4 distinct layers, each with its own job. The top layer, the application layer, is all about what we're doing, things like browsing websites, HTTP, or sending emails, SMTP. Below that, the transport layer makes sure our data gets delivered reliably, whether it's a quick message or a large file. Then comes the network layer, which figures out the best route for the information to travel. And finally, at the bottom, the link layer handles the actual physical transmission of data, like sending it over Wi-Fi or Ethernet cables. Each layer builds upon the one below it, creating a seamless flow of communication between devices. Okay, let's talk about network models. We have 2 main ones, the OSI and the TCP/IP. Think of the OSI model as a really detailed blueprint. It breaks down all 7 layers of how data gets from your computer to a website, like email or browsing. It's great for understanding concepts, but rarely implemented exactly that way in real systems. The TCP/IP model is the workhorse of the internet. It's simpler with just 4 layers, and it's what actually makes everything connect. The key difference is that OSI has distinct layers, while TCP/IP is more about how things function. Both models help us understand how data travels across a network, but they approach it from different angles. Let's talk about TCP. It's a really important protocol for how data travels across the internet. Basically, TCP is like a super reliable delivery service. It sets up a dedicated connection before sending anything, making sure every piece of information gets there safely and in the right sequence. It does this through acknowledgements, retransmissions, and error checking, so you don't lose data along the way. And it's smart too. TCP manages the speed of transmission to prevent one computer from overwhelming another. That's flow control. Plus, it responds to network congestion to keep things running smoothly. Okay, let's talk about UDP versus TCP. TCP is like a carefully orchestrated phone call. It makes sure everything arrives perfectly and in the right order, but it takes longer because of all that checking. It's connection-oriented, meaning you have to establish a link first. On the other hand, is more like sending postcards. It's quicker because there's less overhead, but you don't know if they'll arrive, or in what order. Both are important for different types of applications. TCP for things where data integrity is crucial, and UDP for those needing speed. Okay, let's talk about when we would prefer using TCP over UDP. The main difference between the 2 protocols lies in their reliability. TCP is like a super careful courier. It makes sure every single package arrives intact and in the right order. It does this by constantly checking for acknowledgements and resending any lost pieces. On the other hand, is more of a let's just get this delivered quickly approach. It doesn't guarantee delivery or that things will arrive in sequence. So, we use TCP when reliability matters most. Think about browsing websites where you absolutely need all the content to be there correctly, sending emails where losing messages isn't an option, or transferring files where corruption is a major concern. Basically, if data integrity is non-negotiable, TCP is the way to go. Okay, let's talk about when you'd prefer UDP over TCP. while TCP is super reliable, guaranteeing that your data arrives in order. UDP is really focused on speed and low latency. Think of things like live video games or online voice calls where a tiny bit of dropped packet is better than a delayed response. It also shines with broadcasting, sending information to lots of devices at once, like streaming content. Even DNS requests use UDP for quick lookups. And there are some applications, like certain sensor data, that can actually handle occasional lost packets without a problem. So, if speed and responsiveness are the most important things, UDP is often the way to go. Okay, let's talk about the TCP three-way handshake. It's a really important process that happens every time two computers want to have a reliable conversation over the network. Think of it like a phone call. You need to say hello before you start talking, right? The first step is the client sends out a SYN packet, basically saying, hey, I want to connect, and also including a random number. Then a server responds with the SYN ACK packet, acknowledging that it received the request and sending its own random number back. Finally, the client replies with an ACK packet, confirming receipt of the SYN ACK, and boom, the connection is established. It's all about making sure both sides are on the same page before you start exchanging data. Okay, let's talk about how TCP connections gracefully end. It's not like a program just quitting. Instead, it uses something called the four-way handshake. Think of it as a polite way to say I'm done. First, one side, usually the client, sends a signal saying I'm finished sending data. This is called a FIN packet. The other side responds with an ACK, confirming they received the message and are okay to close too. Then, the other side sends their asterisk on FIN, indicating they're done sending. Finally, the receiving side replies with another ACK, and that's it, connection closed. This handshake ensures both sides agree on the closure, which is super important for reliable data transfer. Okay, let's start with HTTP. It's absolutely fundamental to how the web works. Basically, HTTP is like a set of instructions that tells your browser how to ask for things from websites and how those websites respond. It operates on a simple request-response model. You ask for something, a web page, an image, and the server sends it back. It's important to know that HTTP is stateless, which means each request is treated as if it's brand new, no memory of what happened before. We'll talk more about this in a bit. And just to illustrate, here's a very simplified example of an HTTP request. It's all text-based and easy to read. Okay, let's talk about HTTPS and how it's different from the regular HTTP. Basically, HTTP is like sending information over an open road. Anyone can peek at what you're sending. But HTTPS adds a super secure tunnel using something called SSL/TLS encryption. This makes sure that your data, like passwords or credit card numbers, stays private and protected during its journey to the server. It's all about adding that extra layer of protection, making communication much safer for everyone. Okay, let's talk about how HTTPS keeps things secure online. It all starts with a handshake between your browser and the website you're visiting. This handshake uses TLS or SSL to create a protected connection. The server shows its identity certificate verified by a trusted authority, proving who it really is. Then, everything that's sent back and forth gets encrypted using strong algorithms like AES. Think of it like sending a message in code. And importantly, HTTPS also checks if the data has been altered during transmission, ensuring you're getting exactly what you expect. Okay, let's break down the SSL/TLS handshake. Think of it as a really important hello between your browser and the website you're visiting. It starts with the client, that's your browser, sending its own hello. This message tells the server what versions of SSL/TLS it supports and which encryption methods it prefers. The server then replies with its certificate, which is like a digital ID card, proving who it is. The client checks this ID to make sure it's legit. Then, they both agree on how to create a secret key that will be used to encrypt all the data passed back and forth. Finally, they confirm everything worked correctly by sending finished messages. Basically, it's a carefully choreographed dance guaranteeing secure communication. Okay, let's talk about HTTP methods. They are like commands you send to a website. Think of them as verbs that tell the server what you want it to do. We have several common ones. Get is used for simply retrieving information, like reading an article. Post sends data, often used when submitting forms or uploading files. Put replaces an entire resource. Patch makes changes without replacing everything. Delete removes something entirely, and options just asks about how the server can talk to you. Understanding these will really help you build well-structured web applications. Okay, so let's talk about GET and POST in HTTP. Think of GET as a way to politely ask the server for something. It sends information as part of the URL itself, like when you search Google. POST, on the other hand, is more like sending an order. It packages all the data inside the request body, which can be useful for things like submitting forms or adding new content. Okay, let's talk about HTTP status codes. They're like little messages from the web server telling you what happened with your request. Think of them as a code system for successful requests versus errors. We can broadly categorize them into informational 1x, success 2x, redirection 3x, client error 4x, and server error 5x. A 200, for example, means everything's good. The server got your request and is sending back a response. A 404, on the other hand, is like saying sorry, I couldn't find what you were looking for. And a 500, that indicates something went wrong on the server side. Understanding these codes helps you quickly diagnose problems when troubleshooting website issues. Okay, let's talk about HTTP status codes. They're like the server's way of telling you what happened with your request. A 200 OK means everything went smoothly, just as you hoped. A 301 move permanently indicates something has changed and you should update your links accordingly. Then there's a 400 byte request. That's usually a problem on * end, like an incorrect URL. 401 unauthorized means you need to log in or provide credentials. 403 forbidden suggests you don't have permission to view something. And if the server can't find what you're looking for, it sends back a 404 not found. That's your classic page not found error. Finally, a 500 internal server error means there was an issue on the website side itself and they are working to fix it. Okay, let's talk about something really important when it comes to web requests: HTTP headers. These aren't the main part of your request, that's the data itself, but they provide critical context for the server. They're like a set of instructions. We have things like the host header, which tells the server which website you're trying to reach. Then there's the user agent, letting the server know what kind of browser or app is making the request. And don't forget content type. This tells the server what format your data is in, like JSON or HTML. Headers are super useful for developers to understand how their site is being viewed and used. Let's talk about HTTP response headers. They're like little notes attached to the data your browser receives from a web server. They provide vital information, going beyond just saying here's your web page. For example, content type tells the browser what kind of content it is: HTML, JavaScript, or something else. Content length lets the browser know how much data to expect. And headers like cache control and set cookie are really important for things like website performance and remembering user preferences. Okay, let's talk about the host header in HTTP. It's a really important detail when understanding how web servers work. Basically, the host header is like giving the server a clue. Hey, I want to see this website. It tells the server exactly which domain or resource you're requesting. This is particularly useful for something called virtual hosting, where one server can handle multiple different websites. Think of it like having several separate web pages all served from the same physical location. The server uses this header to figure out which specific website configuration to load and serve. Okay, let's talk about cookies. Imagine you're logging into a website without cookies. The site would forget you every time you close your browser. Cookies are small files websites store on your computer to remember things about you. They're like little digital notes. A website might use them to keep track of whether you're logged in, what's in your shopping cart, or even just your preferred language. They work by sending a cookie back and forth between your browser and the server each time you visit. There are different types to session cookies that disappear when you close your browser, and persistent cookies that stick around for a while. Do you have any questions about how they're used? Okay, let's talk about sessions. Basically, a session is like keeping track of a conversation between your browser and the website it's visiting. Instead of repeatedly asking for all the information needed, like whether you're logged in or what items are in your shopping cart, the server remembers who you are for a little while. It does this by sending a unique identifier, usually a cookie, back to your browser. Then, every time you make another request, that cookie is sent along with it, and the server uses it to retrieve all the information related to your * session. This makes things faster and gives users a more seamless experience. Okay, so when you're browsing the web, your browser is constantly talking to servers. Initially, each time you want a new page or image, it has to set up a brand new connection, like making a phone call. That takes time and resources. But HTTP uses something called persistent connections, which is essentially saying, hey server, let's keep this connection open so we don't have to start over every single time. It's like having a conversation where you don't need to dial the number again each turn, just carry on talking. This significantly speeds things up because all those extra steps of negotiating and setting up are skipped, making your browsing experience much smoother. Okay, let's talk about HTTP/2 and how it makes the internet faster. HTTP/1.1 had some serious problems, primarily that if one request took a while to complete, everything else had to wait in line. It's like a single-lane highway. Also, all those headers were repeated with every page load, wasting bandwidth. HTTP/2 fixes these issues by allowing multiple requests and responses to happen simultaneously over a single * connection. It's like having multiple lanes on the highway. Plus, it compresses the headers so they don't take up as much space. And finally, the server can even proactively send resources that it anticipates you'll need, saving you time waiting for those requests. Okay, so let's talk about the big difference between standard HTTP and HTTP/2. Think of it like this: HTTP 1.1 was a bit clunky, it used separate connections for every little thing. This meant if one packet got lost, everything else had to wait. HTTP/2 changed all that by allowing multiple requests to be sent over a single connection at the same time, kind of like merging several lanes into one. Plus, it compresses headers and can even push resources to your browser before you even ask for them. It's really designed to make web browsing faster and more efficient. Okay, let's talk about keep alive in HTTP. Basically, the internet isn't just one big conversation, it's a bunch of little back and forths between your browser and servers. Normally, after you load the web page, the connection is closed. But with Keep Alive, the server keeps that connection open so you can make multiple requests without having to establish a new connection each time. This dramatically speeds things up, reduces server strain, and makes for a much smoother browsing experience. It's a really important concept to understand when thinking about web performance. Okay, so content negotiation is all about figuring out how best to deliver a web page or other resource to your browser. It's like a little dance between the client, your browser, and the server. The browser tells the server what formats it can handle, and the server responds by saying, "Here's what I offer." The browser then picks the format that both sides agree on. This ensures you get the resource in a way that works best for **U**, considering your capabilities and the server's choices. Okay, let's talk about CORS. It's a really important security feature in web browsers. Basically, it stops one website from just randomly grabbing data from another website, which could be risky. Think of your homepage domain trying to get information from a completely different website domain B. Without CORS, the browser would usually block this because it's a potential security hole. But CORS provides a way for those two websites to talk to each other safely. The server sending the data sends an access control allow origin header, telling the browser exactly which sites are permitted to access that information. It's like giving permission slips. It's how API and many modern web apps can work securely together. Okay, so URL, think of them as addresses for websites. They have several parts working together to lead you exactly where you need to go. First up is the protocol, which tells your browser how to talk to the server, usually HTTP or its secure version, HTTPS. Then comes the domain name, that's the recognizable website address like google.com. Next is the path, which indicates the specific page or resource on that site, like about our product. Sometimes you'll see query parameters added to the end of a URL. These are used to pass information to the server, almost like adding extra instructions. And finally, there's a fragment identifier. This allows you to jump directly to a specific section within a web page, kind of like bookmarking a particular part. Okay, let's talk about query strings. They're a really important part of how URL work, especially when you're dealing with searches or any kind of dynamic content. Basically, they are the bits after the main URL path starting with a question mark. They're made up of key-value pairs, like instructions for the server. For instance, in this example, https://www example.com/search, q equals network plus protocols and sort equals relevance. Q is the key and network plus protocols is the value it's telling the server you want to search for network protocols. And sort is another key with relevance as its value. They help the web server understand what you want. Okay, let's talk about DNS. It's super important because it lets us use easy to remember website names like Google instead of complicated numbers. Basically, DNS is the internet's phone book. It translates human-friendly domain names into the IP addresses computers actually use to communicate. When you type a URL in your browser, it first asks its configure DNS resolver. This resolver then goes through a chain of queries, starting with root servers and working its way down to the authoritative name server that holds the specific IP address for the website. It's all about making things easier and more user-friendly. Okay, let's talk about IP addresses. Basically, they're like your computer's mailing address on the internet. Every device that connects phones, laptops, even your smart fridge needs one. It's a unique number that tells data where to send itself. We have two main types, IPv4 and IPv6. IPv4 uses numbers from 0 to 255 separated by dots, like 192.168.1.1. And IPv6 is the newer version, using longer hexadecimal numbers. The point is, without an IP address, data packets wouldn't know where to go. They're fundamental to how the internet works. Okay, let's talk about IPv4 versus IPv6. Think of them as two different versions of our postal code system. IPv4, which we've been using for decades, has a limited number of addresses, basically enough for a few billion devices. It uses a dotted decimal format like 192.168.1.1. But the internet is growing rapidly, and those addresses are running out. That's where IPv6 comes in. IPv6 has a huge address space, almost limitless, thanks to its 128-bit structure. It uses hexadecimal notation. You might see something like 2001 debate 8503 8 3707 334. It's more complex to read, but it provides the space we need for everything from your phone and laptop to smart appliances and IoT devices. IPv6 also has some built-in security features that weren't as prevalent in IPv4. So, fundamentally, IPv6 is a much more future-proof system. Okay, let's talk about subnet masks. They're like fences defining the boundaries of each section of your network. Imagine an IP address, it's a unique identifier for every device. A subnet mask tells you which part of that address identifies the network itself and which part identifies the specific device * with an * that network. It works by combining the IP address and subnet mask using a bitwise AND operation, revealing the network portion. Knowing your subnet mask is key to routing data effectively and keeping things organized. Okay, let's talk about an AT network address translation. Basically, it's like a translator for your home or office network when it connects to the internet. Because there aren't nearly enough public IP addresses available, an AT allows multiple devices on your private network to share *1 * single public address. Your router handles this translation process, swapping out the internal IP addresses with its own public one. This is especially important because most home networks use PAT, which means many different devices are all using the same public IP address by assigning them unique port numbers for their connections. It's a clever way to make things work efficiently and adds an extra layer of security by hiding your network's details from the outside world. Okay, let's dive into firewalls. They're like security guards for your computer network. Basically, examine all the data coming in and out and decide whether it's allowed or blocked based on a set of rules. It's really about filtering traffic, looking at things like IP addresses, ports, and even the type of information being sent. Some firewalls are pretty simple, just checking basic details, while others are much smarter and remember what's happening over time. Protecting your network is vital, and firewalls play a huge part in doing that. Okay, let's talk about proxy servers. Imagine you're trying to get something from the internet, a website, a file, anything. Normally, your computer directly asks for it. But with a proxy server, there's an extra step. It acts like a go-between, taking your request and sending it on to the destination. This offers some real benefits: security by hiding your IP address, faster access through caching frequently used content, and even the ability to block certain websites if needed. Think of it as a helpful gatekeeper for your internet activity. Okay, let's talk about reverse proxies. Imagine you're trying to get somewhere in a busy city. Instead of going straight to your destination, you first go through a central information booth. That's essentially what a reverse proxy does. It sits between the outside world, your client, and your web servers. It takes all incoming requests and then intelligently forwards them to the correct server. This brings a lot of benefits. It boosts security by hiding your internal setup, helps distribute traffic so no single server gets overwhelmed, can speed things up by caching frequently requested content, and even handles the complicated job of encrypting data. Okay, let's talk about load balancing. Think of a load balancer as a super smart traffic cop for your servers. It sits in front of multiple web servers, making sure that no single server gets overwhelmed with requests. This is really important for ensuring websites and applications are always available. It works by directing client requests, things like HTTP or HTTPS requests, to the most appropriate server at any given time. The load balancer uses protocols like TCP/IP to establish connections with those servers, but its job is to distribute traffic intelligently based on algorithms. It's a vital component for building scalable and highly reliable systems. Okay, let's talk about VPN, virtual private networks. Basically, a VPN creates a secure private connection for your internet activity. It's like building a secret tunnel through the public internet. When you connect to a VPN server, all your data travels through that encrypted tunnel, so websites only see the VPN server's address instead of yours. This helps protect your privacy and keeps your information safe, especially when using public Wi-Fi. They also let you access content that might be blocked in your location. Okay, let's talk about port forwarding. Essentially, it's like creating a secret route for internet traffic. The router acts as the gatekeeper, and when someone tries to reach your computer on a specific port, say the standard port for web servers, the router intercepts that request and sends it directly to the correct internal address. This lets you share services like websites or cameras with people outside your home network safely. It's super useful if you want to host something yourself or access devices remotely. Just remember, good security practices are important when setting this up. Let's talk about latency, often described as the delay in a network connection. It's essentially how long it takes for data to travel between 2 points, measured in milliseconds. Imagine shouting across a valley. There's always a little bit of a pause before you get an answer back. This delay can really impact your experience. Websites load slower, online games feel laggy, and video calls become choppy. Basically, any application that uses the network will be affected by high latency. Let's talk about packet loss. It's when data packets don't make their way to where they need to go, and that can really mess things up for reliable communication. It happens due to a bunch of reasons: overwhelming traffic, equipment problems, or even interference. But the good news is there are ways we can tackle it. We can use techniques like adding extra data so lost packets can be rebuilt, letting TCP automatically send retransmissions when something goes wrong, prioritizing important data during busy times, and upgrading our network hardware to ensure everything's running smoothly. Okay, so you're wondering how your emails, videos, and web pages actually get from one place to another. Well, it's not like a single, direct route. It's more like sending a really complicated letter. The internet uses something called TCP/IP. Think of it as a set of rules for how information is broken down, sent, and put back together. First, the data starts with the physical layer, which is just about getting the signal from one place to another like electricity through wires or radio waves. Then it moves up a few layers. Each layer has specific jobs. The network layer handles addressing so packets know where to go, and the transport layer makes sure everything arrives in order. Finally, protocols like HTTP/HTTPS are used for things like web browsing. But here's the really cool part: data is broken into small pieces called packets. These packets travel independently across different networks. Your home router sends one packet to your ISP, which then sends it onto another router, and so on. The receiving computer puts all those packets back together to form the original message. It's a clever system that allows massive amounts of data to flow seamlessly around the world. Okay, let's dive into something called MTU, Maximum Transmission Unit. It's a really important concept for understanding how data travels across networks. Essentially, the MTU is like the biggest box you can send through the internet without having to break it up. It includes everything: the address information and the actual data itself. When a packet gets bigger than what a router or network link can handle, it has to be divided into smaller pieces, which takes time and can sometimes cause problems. Ethernet typically uses an MTU of 1500 bytes, but things like VPN can reduce that even further. Understanding this helps us make sure the internet works smoothly. Okay, let's talk about packets. Basically, a packet is just a little chunk of data that's sent across the internet or any network. It's like breaking down a big message into smaller, manageable pieces. Each piece has a header. Think of it as an address label and instructions that tells the computer where to send it and how to put it back together. Then there's the payload, which is the actual data itself, like your website request or email. And get this, packets can sometimes arrive out of order because networks aren't always perfectly reliable. So, each packet is a number, so the receiving computer knows exactly where it fits in the bigger picture.